So, as mathematical objects, limits follow certain rules that most mathematical objects do, and these are called limit properties, and there are quite a few. Most of them are pretty intuitive. That's fine. Nope, that's Control N makes a new presentation. Okay. Okay, so when we say that a limit equals, some value L, what that's actually telling us is that every limit that you see, aside from the infinite ones, also the ones that don't exist, every limit that you see is a number. Limits are numbers. Limits, like this limit statement right here, this expression represents a number. If it exists. Okay, and because they represent numbers, they can be combined in the way that numbers usually can. So in no particular order, here are some of the properties that limits are subject to or that they follow. So let's see. Okay. So if you have two different limits, so if you have, say, a limit as x approaches a of a function f of x, and we'll say the two numbers that I usually use. We'll just say that that equals L. And you have separate limit of a different function approaching the same target value, like x approaches a in both of these limits, but this limit is of the function g of x, and perhaps it equals a different number. It could equal the same number, but it could also be different. And we'll call that k. So these limits both exist. They both equal finite numbers. Maybe what they equal is the same. Maybe it's not. Doesn't matter. If that's true, then the limit as x approaches a of the sum of these two functions is just the individual limits added together. You don't have to write this middle step, I guess. But essentially just saying that you can break the terms of a limit up into separate limit statements if you want. And it's going to equal whatever the limit of the first thing is plus whatever the limit of the other thing is. Okay, and this is called the sum property. And actually, because I'm feeling kind of lazy and I don't want to write the whole thing over again, just go ahead and wherever there's a plus sign, make it a plus or minus. And just say that this is the sum and difference property. Okay, so any linear combination of functions can be broken up into separate, a linear combination of separate limit statements. Okay, if you have the limit of a product, so a limit of a product will equal the product of the limits. So it's just like you're taking the two separate limits and multiplying them together. The limit as, there we go, the limit as x approaches a of g of x, which just equals L times k. And as you might expect, this is called a product property. And like looking at these, it's not like you'll have to explicitly remember each of these. Like you're never going to be asked to write out like there's never going to be a question where it's like write out the sum property. So it's not like you have to memorize these. Just know that this is a thing that you can do with limits is break them up in this way. All right, the next one is the quotient property, and that's just going to happen if you have a limit of one function dividing another. All right, so the limit of the quotient is going to be the quotient of the limits. So that's going to be L dividing K. So long as K does not equal 0. So long as that bottom limit there isn't 0, because at that point you're dividing by 0. Okay, so you got sum, differences, product, and quotients. And then one last one. Okay. Just one last one, sort of shoving quietly at the end here. If if you're trying to find the limit of a constant times f(x), this here is some sort of constant multiple. Then you're free to remove that constant from the inside to the outside of the limit statement if you want. So that ends up being, if you move to the outside, that ends up being c times the limit as x approaches a of f of x. Yeah. Which just equals c times l. So you can move constant multiples out of and into limit statements as much as you want. You can't remove anything with an x, but if you're multiplying, if it's a constant, rather than a variable, you're totally free. They're multiplying it. You're totally free to multiply them in and multiply them, and divide them out as much as you want. This is just called the constant multiple property. Okay. There are others that we'll touch on later, but for now, we'll use these 5. Yeah, I guess technically there are 5. That first one is technically 2 separate ones, kind of. To figure out from a graph what a particular limit might be that we can't see directly. Okay. So we're going to use this figure, this graph. This graph where the red function is this function f and the blue function is the function g. To figure out these 3 limits. Okay. So for part A, we're looking at the limit as x approaches -2 of this linear combination of functions, f of x plus 5 times g of x. So first of all, we're concerned with what's happening when x is -2. So we're concerned with the limits of the functions around here. But before we even look at the graph, we can break this up. Into this. It's a sum. We can break up a sum. And this 5 that's in front of the g, we can take it out from the limit statement that it's going to be a part of. So we could rewrite this as the limit as x approaches -2 of f of x plus 5 times the limit as x approaches -2 of g of x. It's almost like we're distributing the limit statement over addition. Okay, now instead of a single limit statement of a complicated, sum of terms, we're just left with, more terms, sure, but simpler limit statements. Now, what is the limit of f of x as x approaches -2? F is this red graph here. What value does the graph approach not what it actually is, but what does it approach as x moves towards -2? Yeah, 1. 1. It, -2 is right here, so from both sides it approaches a y value, or a function value of +1. So this is just 1. Oh, see, this is 1. And what about g? What value does it approach as x moves towards -2? Yeah, there's no hole here or anything. And coincidentally, it does end up also having a function value of -1, but that's also the limit, because it's a nice continuous function. So this is -1. So what we have is 1 plus 5 times -1. So that's 1 minus 5, which is -4. The alternative way to do this, and what we're trying to avoid, is literally making a graph for the entirety of f of x plus 5 times g of x. Like, we could make a separate graph there, and then just like look at that graph that we hypothetically make. But you don't want to have to take f and g and combine them in this way and then draw out what that is. Okay, so we'll do b now. We're looking for the limit as x goes to 1 of f times g. So given that that's a product, we can break it up as a product of individual limits. We can rewrite this as the limit as x approaches 1 of f times the limit as x approaches 1 of g. And then just find these individual limits and then multiply them together to find this. Okay. I'll find out what those are and multiply them together. So we're no longer interested in what's happening around -2. We're interested in what's happening around x equals 1. Okay. So what value does f appear to be approaching as x gets really close to x equals 1? 2, yeah. On the other hand, what value, if any, is g of x looking like it's approaching as x gets close to 1? What does it look like it's approaching from the left? -2. But what does it look like it's approaching from the right? -1. Those are different. The left and right-handed limits are different there around x equals 1. So does a general limit for g exist at x as x approaches 1? No. This does not exist. So a limit that is 2 times a limit that fails to exist results in a limit that fails to exist. So this limit described in b does not exist. Okay, then last we'll do this quotient, where we're looking at a limit of a quotient of functions, we can break that up as a quotient of individual limits. So we can break that up as the limit as x approaches 2 of f, so we're looking at f, divided by the limit as x approaches 2 of g. And so we're concerned with what's happening around x equals 2, which is this area right here. What is the limit of f as x approaches 2, like approximately? Sort of best guess as to where that crosses. Yeah, maybe like, I don't know. I'm gonna say 1.4. Or so. What about g? What's the limit as x approaches 2 of the function in blue? What function value does it appear to be approaching, both from the left and the right? 0. So we got ourselves 1.4 divided by 0. That is undefined. And so the limit described in C, also fails to exist. Yeah, we'll say the limit as described in C does not exist. Okay, so there are some other limit properties, relatively straightforward ones as well. Okay. The limit as x approaches a of any constant, so there's no x's here for anything to approach, like the expression is just this constant, it equals c. You know, there's no x in the expression for anything to move closer to a or anything like that. You can also think of this as being like the limit of some constant function. You know, f of x equals c. Where regardless of where you move on the x-axis, the value of the function is just c. So this is a constant property. So as an example, I guess, the limit as x approaches, I don't know, let's just say 99 of 3 just equals 3. Right, your expression just is the number 3. It's going to be 3 no matter what x is, because there's no x is in the expression. Okay. The next property is that if you're looking for a limit that is just the limit of x, well, the limit of x as x is approaching a, x is moving closer and closer to a, the limit of that x is clearly going to be a. And that can be illustrated by the function y equals x, which is just this, this sort of 45-degree line, right? This is the line f of x equals, you can say it's f of x equals x or y equals x. So if you go to a, if you go towards a on your x-axis, well, it just means that the point that you meet it at is also going to be at a height of a. I forget if this has a name and I'm not going to come up with one, so we'll just leave that side blank. Okay. And this has two extensions. The limit as x approaches a of any power of x is just a to that power. And the limit as x approaches a of any root of x is just that root of a. And specifically, this assumes that n is a positive power or a positive root. No negative powers and no negative roots, because those would flip it into the denominator and all sorts of weird stuff would happen. Now we're going to talk about how we might evaluate limits, like actual limits that equal the actual numbers, maybe without the use of a graph, maybe without the use of a calculator, to make a table. Because that's really what you want to end up doing. The first method, and one that we did, one that we actually did a couple times, and one that you should always try first, if possible, is a method called direct substitution, which just means you take your target value and you plug it in for x in the expression. Okay, continuous, okay. Alright, so we're interested in finding out the limit as x approaches 1 of this expression. So the first thing that we're going to do, and that you should always try to do, is to directly substitute 1 for x. So we're looking at 1 squared minus 1 over 1 minus 1. Numerator is 0, and the denominator is also 0. This is an indication that there's some algebraic manipulation possible. Getting this sort of 0 over 0, what we called an indeterminate form on Monday. And in fact, we can factor this. The numerator here, x squared minus 1, is a difference of 2 squares. So whenever you have a difference of 2 squares, you can do this. You can go both ways with this, but a plus b and a minus b, as two separate factors being multiplied together, will eventually make a squared minus b squared. If you were to fold that out, you'd get a squared minus ab plus ab. Those cancel each other out, and then a minus b squared at the end. So if you ever want to find, if you ever recognize something as a difference of 2 squares and you want to, figure out what it factors into, take the square root of the first square. Square root of x squared is x. And that's the thing that should go in front of both factors. If you want to know what the second term should be, take the square root of the second square. Here the second square is 1. Square root of that is 1. One of these gets a plus and one of these gets a minus. The bottom is still x minus 1. Okay, but having factored that, you might realize or notice that now there is a cancelable factor on the top and the bottom. You can cancel out this x minus 1 on the top and the bottom. You can cancel out any factor that appears both in the numerator and denominator at the same time. And because that factor that we cancel out is x minus 1, that was kind of what was causing both the numerator and denominator to be 0. X minus 1 is what, if you plug in 1 into it, ends up being 0 and makes that happen. So this, after canceling out, just ends up being the limit as x approaches 1 of x plus 1. After doing that sort of simplification, try directly substituting again. Well, 1 plus 1. So you just shove that 1 into that place where that x is. 1 plus 1 equals 2. So the limit that we're looking for is just 2. And actually, if you were going to draw out this as a graph, this is what it would look like. 1. Sure. Okay. And how I know that is because after this simplification, it ended up being x plus 1. The function, y equals x plus 1 is just a line with a slope of 1 and a y-intercept of 1. But as originally written, it included this factor on the top and bottom, x minus 1, that caused there to, that caused this stuff to happen. That's known as a hole, and you might remember that from algebra. But it just means that there's a hole at positive 1. But this doesn't really change the shape of the graph otherwise. So really the shape of the graph is fundamentally that of x plus 1, just with the extra hole sort of slapped onto it. And looking at this graph, you can tell that, yeah, as x approaches 1, the function is definitely approaching a y value of 2. Not that you have to draw it out if you don't want to. Okay. This mathematical statement is just sort of saying if two functions are equivalent except at like one, if two functions are equivalent except at the target value, then you can use one to find the limit of the other. The way that we did that was we were trying to find the limit of this, but we use the limit of this instead to find it. And these two right here that I've highlighted are equal to each other everywhere, except specifically at x equals 1. But since they only differ at a point, the limit of x plus 1 tells you the limit of x squared minus 1 over x minus 1. Okay. Right. Limit only exists if both exist. Squeeze theorem. Maybe we can skip the squeeze theorem. It'll depend on what's on the homework. Okay. So we're going to show that the limit of the absolute value function as x approaches 0 is 0. I guess you could directly substitute it, but the absolute value function is kind of a weird one, so that wouldn't necessarily be a guarantee. And this is, although you dealt with the absolute value function in, your algebra class and probably some of your pre-calc classes, it's possible that you never talked about what it really means. Now, the absolute value function is the function that's defined as follows. It's a piecewise function. The absolute value of x, or of anything really, the absolute value of anything is if x is negative, it equals the negative of that negative number, turning it into a positive. So it equals negative x if x is less than 0. However, if x is positive, then you just use the number as it is. So what this means is that, like, if you got x and it's negative 5, the absolute value of it should be the flipped version of that, so negative 5, so positive 5. This basically takes any negative number and turns it positive, and leaves positive numbers as they are, which, as you're aware, that's what the absolute value function does. You can take any absolute value statement and sort of write it out as a piecewise function this way. And so we just have to verify that these two one-sided limits are the same as x approaches 0. So we want to say that the limit as x approaches 0 from the left, so from the negative side, we're looking at negative x if we do that, if we're approaching from the left. And well, just through direct substitution, that's 0. And likewise, we want to verify that approaching from the right of 0, for which we'll use this sort of second thing here, because if we're approaching from the right of 0, we're approaching from the positive side. That is also 0. So these one-sided limits are both 0. So the limit as x approaches 0 in general of the absolute value function is 0.